Welcome to July of Calculus. Here we depart from the realm of mortals and ventures into the infinite.
You're sounding like Akko there.
Why wouldn't I sound all bombastic or whatever? This is such an important milestone. I even wrote a script for us to go off of.
A script? I guess I could read off of it.
That wasn't part of the script.
Okay, so let's start off slow. What's the question for today?
Well, I've been preparing this one for a while. Today, we are gonna look at the wild world of differentials and what happens if we treat dy over dx as a fraction.
May you remind me what a differential is?
That's exactly what today's problem is.
Also, treat dy over dx as a fraction? I thought it was just written like that as notation.
Yeah, I know, bit of a bizarre thing. Anyways, let's get started. First, let's take a step back for a moment. There are several ways to represent a derivative. The one we are interested in today is called Leibniz's notation. As you can see, it kind of looks like a fraction, but you and I already know that.
Yeah, the chain rule makes it look like you're cancelling out a fraction as well. But we're getting ahead of ourselves. This is not actually a fraction, it's just a notation we use.
Yeah, I know, but you may have also seen it written like this. As you know, or for those who don't know, f prime of x is another way we can write the derivative of the function f of x, which here we're letting it equal to y.
I feel like this is just an abuse of notation. Surely this doesn't mean multiplying both sides by dx.
It does actually.
Wait, what?
Let's review the definition of the derivative. The derivative is defined as the limit of the slope of the line between 2 points of a function getting closer together. In maths language, it is written like this.
Hey, that's different from the definition I learned. My definition looks like this.
Well, both of the definitions are the same if you let delta x equals x minus a.
I see. When you look at it like this, it makes sense that the derivative could be written as a fraction of two components. Maybe we can let dx be the limit as delta x approaches 0, delta x, and dy be the limit of f of x plus delta x minus f of x.
F of x plus delta x minus f of x can also be written as delta y, which may be useful in the future. Unfortunately, both of these are approaching 0, so it wouldn't work. Even if the limit of the quotient approaches something, that doesn't mean the quotient of the limits do.
So, what can we do?
Well, let's bring back the thing we've seen from before. The one we both thought was just alternate notation. Now, Sayo, what can you do to turn this from an abuse of notation into an actual definition for d of y? No, dy, not d of y. Sorry, can we cut this out?
Leave it in. Anyways, we can define dy as the limit of delta x approaching 0, f prime of x delta x. But wait, we're still just defining 0 by 0.
Not if we remove the limit sign.
Oh yeah, now that we have defined dy like this, the ratio between the stuff inside the limits remain constant. And now if dx is non-zero, then dy is also non-zero. But then, it doesn't feel like an infinitesimal anymore, it's just a very small number.
Okay then. Remember that delta y over delta x approaches f prime of x as delta x goes to 0. This means that delta y over delta x equals f prime of x plus epsilon, where the error term epsilon gets closer to 0 as delta x goes to 0. Just so we can be sure that this is actually the derivative of y with respect to x, let's take the limit of both sides. As you can see, the left side is the definition of the derivative and the error of the right side vanishes.
I don't see where you're going with this.
Well, why don't we multiply both sides by delta x? Here, we get f prime of x delta x plus epsilon delta x. Which of these two parts tends to 0 faster?
Well, f prime of x doesn't depend on delta x, but epsilon does. So f prime of x delta x is the one that remains. Hey, this is just dy. From this, we can say that dy and delta y get closer and closer to each other as delta x gets closer to 0. So I guess in a way, the limit of delta y is dy.
Not in the script, but I'll take it.
To be fair, a lot of things we said aren't in the script.
As a bonus, if we let f of x equals x, we get the definition of dx. I want to show you something else. Now that we have an equation, we can add an integral to both sides. The left we can rewrite as the integral of 1 dy, and the answer of this integral is just y, since the derivative of y with respect to y is 1.
Wait, did we just prove the fundamental theorem of calculus with the fundamental theorem of calculus?
Yeah, I kind of just realized that. So, why don't we prove the fundamental theorem of calculus? Let capital F of x be equal to the definite integral from x to 0 of f of x. By the definition of the integral is equal to this. Let's remove the limit for now. Now, if we just extend the bounds of x by delta t, this is the same as adding another rectangle to the area under the curve. So we add f of x delta t to the other side, substituting capital F of x plus delta t and f of x in, then rearranging. It is almost equal to f of x, and if you let delta t go to 0, it ends up equaling it.
Wow, I always knew about the fundamental theorem of calculus, but I never had it explained to me like this.
You can all thank the calculus textbook I have in my room.
How did we get from defining differentials to proving the fundamental theorem of calculus?
Yeah, it's mostly just to pad out the video. I have no idea what I'm doing when writing this script. If you want a better video about differentials, then check out this video by Zundemon Theorem. Hopefully next video would be better. I'll see you then.